Hello guys, welcome back to video lecture series that we are making on assignment questions. In this video, we will be learning about fourth and fifth questions. Okay, coming to fourth one, part A. Question that I have mentioned is explain how to measure attenuation in optical fiber system. Coming to measurement of attenuation in optical fiber system, there are many ways to measure optical fiber communication systems attenuation. Here we will be observing only one method according to your syllabus. First point we have written is signal attenuation is one of the most important properties of an optical fiber because it mainly determines the maximum repeaterless separation between transmitter and receiver. That is, if the attenuation is less, then repeaters will be used in less quantity. If the attenuation is more, then repeaters will be increased. Number of repeaters between transmitter and receiver will be increased. As the repeaters are expensive to fabricate, install and maintain, therefore fiber attenuation has large influence on system cost and equally important on signal distortion. That is, due to attenuation, one is signal distortion will occur, the other one is cost of the system is going to increase because you need to have repeaters and they are expensive in manufacturing, installing and maintaining. The distortion mechanism in a fiber cause optical signal pulses to border as they travel along the fiber. The distortion, what the distortion is going to do is it is going to cause if optical signal pulses to broaden. Okay, this is not broader, this is broaden. This is broaden as they travel along the fiber. When the pulses travel sufficiently far, they eventually overlap with neighboring pulses, creating errors in receiver output. As they are traveling sufficiently far distance, initially signal that we expect is in this nature. Now, as they are traveling far and far, these signals will be broadening and they will be overlapping with each other. This signal distortion mechanism limits the information carrying capacity. In order to avoid this, we need to create more space between each pulse. If the space is increased, then bandwidth consumption is more. As the bandwidth consumption is more, information transmission capacity is going to be decreased. For determining attenuation in fiber, three major techniques are used. One is cutback technique, insertion loss method, and the other one is OTDR trace. So, in this, according to your syllabus, we will be learning about OTDR trace. Attenuation measurement in optical fiber system using OTDR method is as follows. Next point we have written is OTDR stands for optical time domain reflectometer. What does OTDR stands for? It stands for optical time domain reflectometer. It is an optoelectric instrument used to measure the characteristics of the optical fiber. It is an device used to measure the characteristics of optical fiber. It gives an idea of abnormalities or faults in the cable. It is going to provide the idea of abnormalities, what kind of abnormalities are present in the fiber. It also used to measure the signal attenuation passing through optical cable as well as to measure the length of the cable under test. So it also used to measure the attenuation that is occurring in the cable. If there are discontinuities in the optical cable, then scattering of light takes place. If there is any discontinuity, then scattering occurs. Especially when there is a change in refractive index, then light passing through the optical cable gets scattered. If there is a change in refractive index, light will be scattered. Some of the scattered light moves towards the source. That means in backward direction. That is, if this is your fiber and light is being traveled in this direction, and if scattering occurs at this point, some light will travel in forward direction, some light will travel in backward direction. It is called backscattering. The light signal which is traveling in back direction is backscattering. OTDR uses this backscattered light to make its measurements. So OTDR works with the help of this backscattered light. The amount of light which is backscattered is used to calculate what is the loss that is occurring. A pulsating laser generates optical pulses using optical circulator or directional coupler. These pulses are passing to the optical cable. Circuit is used to generate optical pulses and these pulses are passed on to the cable. In the optical cable, due to various reasons, scattering of light takes place. Scattering of light occurs due to different reasons that we have studied in our attenuation concept. Again, using optical circulator, this backscattered light is passed to the optical deflector. Using signal processing block, the signal is converted into proper form. This is proper form of display. Proper form of display. So here you can observe this is your circulator, which is transmitting this back to photodetector, and the signal processor is used to get a proper form, and then you will be getting your display. Initially, light is traveling in this direction and scattered light comes back in this direction. Now your OTDR display contains a vertical axis as you are seeing over here and a horizontal axis like you are seeing over here. Vertical axis has optical attenuation in terms of dB. This axis contains optical attenuation in terms of dB. Horizontal axis has distance in kilometers. Different losses are shown here with different events. Here you can observe different events that are causing the losses. One is reflective event front connector. First connector is going to be reflective in nature. Then occurs fusion splice. If there is a splice, it is non-reflective, but there is some loss. And then comes non-reflective event micro bending. Then there is a bending, and this is non-reflective event. Then comes one more connector. It will be reflective event. Then comes the end of the fiber. Fiber fault location by OTDR. How are we going to locate the fiber fault using OTDR? Applied input pulse gets reflected from the front end and far end of the cable. So from the front end and the far end of the cable, it is being reflected. The time difference between these two reflected pulses is measured. So the difference of time between these two pulses is measured and it is denoted by T. Then the distance of break point from source is given by. Now the distance from this point to this point is given as D is equal to C into T by 2N, where C is speed of the light, T is time taken, and distance traveled by 2 times of N. Actually, it is forward and reflected distances. So it is taken as 2 times of L, where N is your core index. Okay. Here the N that we have written is core, refractive index of the core. OTDR dead zone. What do you mean by OTDR dead zone? Whenever there is a strong back reflection from optical cable, then the photodetector measures it. If there is a strong back reflection, OTDR is going to measure that. During this time period, if there is another back reflection, then the photodetector cannot measure it. If there is one pulse which is very strong in nature, and at the same time there is one more pulse which is weak, then this pulse will not be measured by your photodetector. So this concept is called OTDR dead zone. The other pulse we are ignoring, so it is called as OTDR dead zone. Attenuation measurement by OTDR. How to measure attenuation using OTDR? The display OTDR measures the distance and loss between two markers. We are going to have two marker locations where the OTDR is measured during the attenuation. To measure the attenuation for a particular length of the fiber, the markers are inserted into the fiber, one over here and the other one over here on either end of the fiber. The OTDR gives the measurement of distance between these two markers, like we have said in the previous, where we have calculated the distance between the fibers starting end and ending end. Here we will be calculating distance between first marker and the second marker. OTDR also gives the difference between power levels of these 2 points. In these 2 points, if there is any power deviation, it is also going to mention that where markers are inserted. Thus, attenuation per unit distance can be measured. It is obtained by dividing the power loss by a distance. So total power loss is calculated and it is divided by the complete distance in order to obtain per unit. Now coming to the other question, that is 4B, what I have asked for is explain the procedure of attenuation measurement in microwave communication system. So here I have asked for what is the procedure in which we are measuring attenuation in microwave communication system. Previously we have observed the measurement of attenuation in optical communication system. Now we will be observing the attenuation measurement in microwave communication system. Microwave components and devices always provide some degree of attenuation. They will always provide some degree of attenuation. Attenuation is defined as the ratio of input power to output power and is normally expressed in decibels. What are the units? Units are decibels, and formula for calculating attenuation is equal to 10 log 10 to the base P in by P out. So P in is your input power, P out is output power. Attenuation can be measured by following two methods. One is power ratio method and the other one is RF substitution method. Coming to power ratio method, this method involves measuring of powers P1 and P2 with and without a device whose attenuation is to be measured. Okay, so here what we are doing is P1 is measured without providing a device. P2 is measured with the help of the device whose attenuation is to be measured. After calculating P1 and P2, we are obtaining the ratio of those two powers and we are expressing it in decibels, and using the previous formula, we'll be calculating attenuation. So here you can observe the microwave test bench setup where the first block is microwave power supply, second block is klystron mount. From the power supply, klystron mount is going to take the energy and it is going to provide a signal, and this signal has been attenuated with the help of an attenuator. Then comes frequency meter in order to measure the frequency of the wave incoming signal. Then comes a slotted line to which a matched termination is connected, and a detector mount is connected with a crystal detector present inside this detector mount. This detector mount is going to measure the power signal with the help of thermistor present inside this, and this thermistor is going to provide the value to your power meter. Microwave power supply is used to provide required power in order to generate the electron beam. Klystron mount contains the reflex klystron tube, which uses the power from klystron power supply and generates an oscillating microwave signal. Fixed value of attenuation is provided to the device with the help of attenuator. The power meter and thermistor combination is used to measure the initial power of the signal for a fixed attenuation, and it is denoted as P1. Like we have said earlier, one part of this slotted line is connected to the incoming signal, while second part of this slotted line is terminated using a matched termination in order to minimize or eliminate. This is your eliminate, okay? Eliminate the signal reflections. The third port of this slotted line is used to measure the power signal. Now coming to the other point, the device whose attenuation is to be measured is added between slotted line and the frequency meter, and a new power reading is noted as P2. Now the bench setup is same to the previous one, but only addition is this one, device whose attenuation is to be measured. Again, now what we are doing is after connecting this, again we are applying the same values at the input side and getting the output, and this is noted as P2. Now we have P1 and P2, so we will be substituting this in the formula and calculating attenuation. What are the drawbacks of this method? The power positions indicated by the power meter will lie on the non-linear characteristics of the crystal detector present inside the detector mount. Here the problem is the power positions indicated will depend on the crystal detector present in the detector mount. Due to this, the powers measured and attenuation calculated will not be accurate, particularly if the attenuation of the network is large and if the input power is low. So due to the crystal detector which is present, there are some inaccurate values that are coming out. In order to avoid this, we will be going for RF substitution method. In this method, we measure at a single power position. We will be taking only a single power position. Instead of taking two values, we will be taking only one value. In this method, the power P is measured by placing the device whose attenuation is to be measured. This has placed initially. Now the device whose attenuation is to be measured is replaced with a precision calibrated attenuator. So initially we have placed the device. After placing the device, what we have done is we have taken power value. Now what we are going to do is we are removing this. Instead of this, we will be placing one more attenuator which is calibrated and it is variable. This attenuator previously present is fixed. We are going to fix a value to this. Now here we are going to vary the attenuation. Now the device whose attenuation is replaced with precision calibrated, which can be adjusted to obtain the same power as measured in the initial setup. Previously, we have got a value for power. Now what we are going to do is we'll be varying this variable attenuation value so that we can obtain the previous power value. Under this condition, the attenuation is read from the precision attenuator that would provide the attenuation of the device directly. At the power that is required, we can observe the value from the attenuator and we can take down as the attenuation which is occurred in the previous case. Now coming to the other question, that is 5A. In 5A, I have asked about drawing the basic block diagram of the micro test bench setup and explaining each part of it. Coming to the basic block diagram, the description of each block of a basic block diagram is as follows. So here in the block diagram, you can observe there are different blocks which are useful in order to make a successful microwave test bench setup. that is power supply, microwave power supply, and then a klystron mount which is connected to attenuator that is connected to your frequency meter and slotted line. This slotted line has 2 ports. One is connected, 3 ports. At the one port is provided for the input, another port is provided to a match terminator. Then comes the third port where the output power is measured with the help of detector mount. So here first block occurred is microwave power supply. Microwave power supply is used to provide the beam voltage. It is going to provide beam voltage, repeller voltage, beam current, and then we can select necessary amplitude modulation that we need to do. That is amplitude modulation and frequency modulation in order to transmit the obtained signal to the klystron for generating a microwave signal. Now the other block is klystron mount. Klystron mounts are used to transmit microwave power from left flex klystron to rectangular waveguide. Okay, it is used to transmit power from this power supply into a rectangular waveguide. This klystron mount is present on top of a rectangular waveguide as you have observed in your labs. Here you will be observing a mount over here. You will be observing a mount over here to which some wires are connected from the klystron power supply. So what we are doing is we are converting the waveform into a rectangular waveguide. We are transmitting this from power supply to rectangular waveguide. Okay. Klystron mounts are designed by a cross-section waveguide. On one end of the waveguide is fitted with a movable short plunger, where you will be seeing a fitted movable short plunger which is used to vary the power supply which is coming from the other side. Variable attenuator. A variable attenuator is a circuit that decreases the strength of the input signal either continuously or step by step without appreciable signal distortion while substantially maintaining constant impedance match. So variable attenuator is going to keep the impedance matched or fixed impedance, and then it is going to decrease the incoming signal power either by step or continuously. And it is used to suppress, majorly it is used to suppress the fluctuations that are coming in the power signal. Then comes frequency meter. Frequency meter is a device used for measuring the repetitions per unit of time of a complete electromagnetic waveform. It is used to measure the deflections that are occurring, and using those deflections, it is going to have your frequency value if it is digital in nature. If it is analog in nature, it is going to use your resonant frequency in order to get the original frequency. Slotted line. The slotted line is one of the basic